as it were, based on the materials that dominated those ages. And so we had the Stone Age, and we had the Bronze Age, and the Iron Age, and then we have Silicon Age, or the Semiconductor Age. And we're still very much in the thick of it. We're still very much discovering the possibilities, and our civilization is evolving faster than it has ever before.
I think the most exciting part of my research is when you get to think about what it is that you think are the physical processes that are happening within your device, and when you implement them experimentally, you actually get to see those come alive, and you can see from your results if that in fact is the case. So I think that's quite an interesting aspect of what we do.
So I work on specifically a PTCDA silicon junction and understanding the exciton processes that happen in that. It's theorized that these hybrid states that are in these hybrid solar cells will react differently than traditional pure organic or pure inorganic solar cells. And understanding those processes and refining our understanding, and then experimentally changing these solar cells to perform better is what my research is on.
Organic solar cells, you typically work with different molecules, and you take a whole bunch of one kind of molecules, and then you take a whole bunch of another kind of molecules, and you put them together, typically by very carefully depositing very thin films of these molecules onto a surface, like a piece of glass, especially coated glass. And then some of those molecules, again, have a greater liking for electrons than the molecules on the other side of the junction. And when we shine light onto this material, and when we photo-excite the molecules, so in other words, the photons that are coming in get absorbed, the molecules get excited, the electrons in those molecules get excited, and when they come in contact with molecules on the other side of the junction, they could jump out of one set of molecules and onto another set of molecules. And when they do that, we get electrical current.
I love being able to read stuff in literature, to learn new things, and then to go into the lab and see those results borne out in an experiment, to do it myself, and then reach the edge of scientific understanding, and then build a model to advance it further, and then to see that done experimentally is really exciting for me.
I think it's important for all engineering students to understand, to an extent, what kind of electronic properties materials can have in order to be able to implement them in any practical application. So I think it's a very essential part of fundamental material science to be able to understand that.
Great.
I hope my work can lead to cheaper solar cells, which will make the solar energy a more widely accepted energy solution.
But the fact is, our civilization is evolving faster than it has ever evolved before, and that's thanks in large part to our communications technologies and our energy technologies, which are a consequence of advances in semiconductors and electronic materials. And we're still very much in the thick of it, and this is where a lot of the action is going to be. And so I cannot think of other more exciting things to study than electronic and optical properties of materials. And I really think this is where a lot of the excitement is.